Hello everybody, I am Scott Bryce. I am the owner and developer of the Math Worksheet Site at themathworksheetsite.com. In this video, I want to talk about one of the worksheets that's on the site. The one in particular I want to talk about is the patterns for hemispheric parachutes for model rockets. And let me give you a little history of how I got an interest in doing that particular worksheet, how it wound up on the site, and then I get a little bit into the mathematics behind it, which I think is what you're really interested in. So let's get going. So my first exposure to model rockets was back when I was in junior high. That would have been, let's see if I can think, X number of years ago, right. We had a class in my junior high called Oceanography and Aerospace, and the kids in that class got to shoot rockets and fly kites and get class credit for it. So we all wanted to take that class. Well, I got into the class and I got a little ambitious. I had a two-stage rocket, fired it off, it went just fine. My kite never flew. I seemed to do better on the oceanography side of things. I had a lot of fun. One weekend we spent down at Bowman Bay at Deception Pass on the Puget Sound, poking around in the tide pools and identifying the little animals we found there. Had a lot of fun. So I did okay in the class despite the fact that my kite never flew. But let's see, fast forward several years, I've got kids now, and I remember back when I flew some rockets and thought it was kind of fun, I'd try it again. So I got a couple model rocket kits and put them together, and got some simpler kits that my kids could put together, and we went out and we flew the rockets, and we had a lot of fun. Now with model rockets, like many things in life, what goes up must come down. But with model rockets, we want to control the speed at which they come down, because if they come down too quickly, they'll be damaged when they hit the ground. If they come down too slowly, they'll drift off in the wind and you'll never see them again. Or you will see them again, but they'll be dangling from a power line or caught in a tree or some such thing. So we want to control the speed at which they come down. The main way we do that with a model rocket is with a parachute. So this is a flat sheet parachute that you would normally get with a model rocket kit. It's a very simple design, it's cheap to manufacture, it's easy to put together, and it gets the job done. But in the May-June 2000 newsletter of the Northern Illinois Rocketry Association, there was an article describing how to create a hemisphere parachute with material cut from plastic grocery bags. And it looks a little more like this. And you'll notice it's made in sections. So these are the sections that are cut out of a plastic grocery bag. And the shape of the section is designed so that as you attach it together at the seams, in this case using a hot iron to fuse the plastic together, the pieces will curl, I guess in a way, form the circular pattern of the hemisphere. You'll see in this one I've got a spill hole, and so as the parachute falls and creates pressure underneath the pressure can be released through the spill hole, and that way the parachute will fall straight down instead of rocking as it releases pressure from either side, and that way it'll fall straight down. Now the reason you would want a hemisphere parachute as opposed to a flat sheet parachute is because for the amount of material in the parachute, the far more efficient. As you can see here in this quick demo, when the flat sheet parachute falls, it's got a bunch of fabric that bunches up and it doesn't catch the air very efficiently, and so it doesn't provide as much drag as the hemisphere parachute that opens up and fills with air and creates a lot more drag for the amount of material as it falls. So the article explained how to create the parachute and the whole process, and gave a rough idea of what each of the gores, the sections of the parachute would look like, but it didn't give an exact shape. Well, challenge accepted. I spent a few days thinking about this. What would the math be to come up with that curve for the shape of each of the gores that make up the parachute, and how would I code that, and how would I put that onto a PDF file and put that up on my website. So I put that together, I put that on my personal website, and people in the model rocket community began to use it. Now during that time I never got to actually build one of these parachutes myself. Life takes you in directions you don't expect to go, and I kind of lost interest in working with model rockets. But if we fast forward a few years, now my youngest daughter is in middle school, and in her science class they're doing an egg drop. Now, if you're not familiar with the way an egg drop works, the students are given an egg, and they need to prepare it in some way by attaching or containing it in something that will cushion its fall, so that when it drops from a particular height, in this case I think it was like 20 feet onto a concrete floor, you want the egg not to break and be damaged when it hits the floor. So many of the students in my daughter's class decided that a parachute would be useful for this sort of thing, but none of the parachutes that they were creating were stable, and so they didn't slow the egg down enough to prevent it from breaking when it hit the floor. My daughter came home and asked me if I knew how to build a parachute that would work for her egg drop, and by golly, I did. So I finally had a chance to put together one of these parachutes, and we worked together that night and put the parachute together, and my daughter's egg was one of 3 that survived the 20-foot drop down onto a concrete floor. So after this successful egg drop, I realized that the parachute is something that might be useful to science teachers or students in a science class, and so I copied the code for the patterns over from my personal website over to the Math Worksheet site, and that's how it wound up there. I've had several people email me and ask me about the math. How did I figure out the shape of the gores? And I'm about to explain that right over here. So here we have our hemisphere. It's divided into sections. These are our gores. And the key to developing our pattern is to find the shape of each section and be able to draw it in a flat surface like this. And so as we attach the various gores together, they will come together at the top and they will form our hemisphere shape, or as close as we can get from flat pieces. So the key then to finding the shape is to find out the width of our gore in various points that are a known distance from the base of the gore up to wherever it is we're measuring our width. And if we do that for enough points, we can take those points along that curve and draw a line that attaches them all together, and we'll have our curve. So that's the key. Now, we can think of our hemisphere here as an infinite number of circles, one stacked on top of the other, each one slightly smaller than the one below it. Smaller by 0, actually, because there's an infinite number of them, but it's 0 in such a way that as we move our way up the hemisphere, eventually they'll become smaller and smaller until the very last of our infinite circles has no size at all. Now, the 0 difference between one circle and the next when we're at the base of our hemisphere is a smaller 0 than the 0 as we move toward the top. Limits are so fun. But just what we need to understand is that we can grade our hemisphere by stacking up a whole bunch of different circles. And so if we can find the size of those circles, the circumference of a circle, at a known distance from the base of our hemisphere, thus the base of our gore pattern, we can find the circumference of our circle. We can use that to find the width of our gore pattern at that same point. And if we find enough of those, we can draw this curve and we can have our gore pattern shape. So to do that, we're going to have to use some trigonometry. But it's going to be trigonometry maybe a little different than what you're used to. The first thing we're going to have to do is take a coordinate plane and drop it right down the center of our sphere. And it'll look something like this. Okay, so here's our coordinate plane. And you can see the curve here is where the sphere intersects with our coordinate plane. The radius of this, we're going to call it 1. Now, my sphere here is actually 12 inches, so our radius is actually 6 inches. But for our purposes here, let's call it 1 radius. Now, you've learned that theta is the measure of an angle in a triangle. And it is. But theta is also the distance traveled around a circle. Starting on the x-axis, where our circle intersects the x-axis on the positive side, we travel up the circle a particular distance, and we wind up at a point x, y. This distance we travel is measured in radiuses of our circle, thus the term radian. We reach this xy point. The x value is the cosine of theta. The y value is the sine of theta. And x and y are also measured in radians, or radiuses of our circle. If we want to translate from radiuses to an actual value in some other unit, we would take our cosine of theta and multiply it by the radius of our hemisphere. And that will give us this x value. Now, if you're used to thinking in terms of triangles instead of circles, I've drawn this out so you can see it. We have our x value here, which is the base of your triangle. We have the y value here, which is the side opposite the angle. We have our theta, which is the measure of our angle. And we can see that our cosine and our sine, see the cosine would be, see I don't do it this way, I think in circles. So our cosine is adjacent over hypotenuse, and in this case the hypotenuse is also the radius of our circle. And so to find our x value here, the length of this line, we would take the cosine of theta, theta being the distance we've moved up around the circle, and multiply that by the radius of our hemisphere. That will give us the length of this line segment right here. That length of that line segment also happens to be the radius of one of our circles. If we can find the radius of this circle, we can multiply 2 times radius times pi. We have the circumference. We divide the circumference by the number of gores, and we have the width of our gore for a particular theta. That is a particular distance traveled from the base of our gore up to where that circle sits on our hemisphere. You can see as we curve this around our hemisphere, you can see how that line corresponds to the circle on our hemisphere. And so that way we can find the width of our gore pattern for a particular distance traveled from the base of a hemisphere up to a known distance up to that point on our gore pattern. If we know the width, we know where to draw these 2 points on either side, and we can find the curve. If we find enough of these points, that is, we find enough of our widths for enough thetas, then we can connect those points together, and that'll give us this curve. The program that I wrote, it does 720 points per inch, and that way the resolution of this curve is actually greater than the resolution that my printer prints, and I always print a nice smooth line. So there you have it. That's the math, and I hope that made sense. I hope I explained it well enough. You can see this is the way I create the patterns for the hemispheric parachute. I'm Scott Bryce for the Math Worksheet Site, and thanks for watching.